I'm sure all of you have seen this image of a black hole by the Event Horizon Telescope. So they're very interesting from the point of view of their physics and also the effect that they can have in galaxies. We know that they are present in the center of the galaxies in our universe. And when we look closely at them, and this is an artist's impression of what you would see around the black hole. So the black hole here is the black sphere, and it's surrounded by gas. So some black holes are accreting gas from their surroundings. So when the gas is flowing into the black hole, it forms an accretion disk while it's inflowing into the black hole. And the process of its accretion disk and the friction between the gas heats up the gas and results in the emission of large amounts of energy towards the galaxy, and it's a feature that we can observe with our telescopes. So when black holes are in this process of accreting gas, they are called active galactic nuclei or active black holes. And the activity here means that they're actively emitting energy to their surroundings. At the same time that we see this energy, the black hole is also growing by the accretion of mass. So you can imagine that the emission of these large amounts of energy are a candidate to affect galaxy evolution. So we think that this injection of energy could potentially affect the amount of stars that galaxies can form, and throughout the age of the universe, black holes could have an important role in affecting their galaxies, or their host galaxies. So this is the problem of black hole fueling. So how do we get this gas, presumably that gas that is in the galaxy, how do we get this gas to the black hole so that it can be accreted and produce this energy that we can then observe? So we know that black holes do this by the accretion of gas. Now the problem is if the gas is further out in the galaxy, and keep in mind that the supermassive black hole is very small compared with the size of the galaxy. We're looking at more than 4 orders of magnitude in physical scale difference. So we need the gas that is in the galaxy, for example, to lose angular momentum in case it's rotating, to be able to flow to the center and then reach the black hole. So we need somehow for the gas to move towards the black hole. And this is the problem of black hole fueling or feeding. How exactly do we do this? How does the gas reach the black hole? If we can answer this question, then maybe we can answer another question, which is why are some black holes active while others are not? So when we look at the galaxies in the universe, a small percentage of them show these active galactic nuclei that I will call AGN for the rest of this talk, but some of them are not active. So not active means that they're not actively accreting gas and emitting energy. So can we understand why this is, why only a fraction of them are active? And according to what we know today, it seems that to fuel a black hole, to feed a black hole, we need two things. First, we need a supply of gas, and then we need dynamical mechanisms that can transport the gas within the galaxy. So these are the two things that we need. So basically, this is the problem of black hole fueling. Now let's look at the galaxies, because these black holes live in galaxies. We saw they need gas to be fueled. The gas comes from the galaxy, and also the active phases of black holes can affect the galaxies in which they live. So galaxies are also an important piece of the puzzle if we want to understand black hole fueling. So what I will be focusing on in terms of the galaxies is when galaxies interact with each other. So that's kind of a particular focus of my work. This is an image from the Hubble Space Telescope. So we know that galaxies can interact. This can be when two galaxies merge to form one galaxy. It could be when they pass very close to each other and there's some tidal interactions and there's some exchange of material between the galaxies. So this is all called galaxy interactions. So what could happen, and we know we've seen this happening in galaxies, is that there could be a transfer of gas from one galaxy to the other. And I will call this, for the rest of the talk, external accretion of gas. So this just means that if you have a galaxy there's a supply of gas coming from the outside environment that is being transferred to that galaxy. And this can be due to an interaction with another galaxy. So this is a way to get an extra supply of gas to galaxies, so with these galaxy interactions. So one very interesting thing, I think it's fascinating, is that sometimes we can get galaxies like this one. So this is an image from the Hubble Space Telescope. And here in the horizontal direction, this yellowish light, this is the stellar body of the galaxy. So this is the main galaxy. But perpendicular to that, you see a distribution of gas and stars. So these galaxies are called polar disk or polar ring galaxies, and they are known because they show these distributions of gas in the polar direction, so perpendicular to the main body of the galaxy. And it's quite striking when you see images like this. So what we can observe is that the distribution of gas is misaligned from the distribution of stars. What happens is this type of galaxy goes through an external interaction, and you can imagine that galaxies interact, different orientations. The gas that is being accreted, so this external gas accretion event, provides gas that ends up in the polar direction of this galaxy. So this is one of the stable configurations that we can get. And when we see something like this 90-degree misalignment between stars and the gas, this is a clear signature that there was an external accretion event, because you can't create these misalignments just by having a galaxy evolving in an isolated environment. So this is the misalignment angle basically measures if you look at the rotation of the stars and the rotation of the gas in this galaxy, they will be misaligned, in this case by 90 degrees. But you can think of different configurations. So if we assume that the angle by which these interactions happen, or along which these interactions happen, is random, then we can end up with an interaction between galaxies where the gas transfer ends up aligned with the stars. So this will be here, this 0 degrees means perfect alignment between the stars and the new gas that came in. It can be 90 degrees, as we saw before, but it could have a wide range of angles, all the way to 180 degrees misalignment. And 180 degrees misalignment is a very interesting case. So it's when the gas that has been accreted ends up in the same plane as the stars, but rotates in the opposite direction. So if you have the stars rotating clockwise, the gas will rotate counterclockwise. So this is called counter-rotation. And I think it's interesting to think that you can have stars and gas rotating in opposite directions in the same galaxy. And this is seen at large scales of the galaxy as well. So we're looking at hundreds of parsecs or kiloparsecs that you see these misalignment angles. So if the misalignment angle is very large, and typically above 30 to 45 degrees, we can say that even with the measurements uncertainties, we're fairly certain that this misalignment between gas and stars came from an external galaxy interaction. Of course, that not all galaxy interactions will result in misalignment. Some of them could end up in the aligned configuration as well. But for the rest of the talk, when I refer to misaligned galaxies, this means galaxies in which stars and gas are misaligned by more than 45 degrees. That's the angle that I will assume for the rest of the talk. And when we see this, we know there was an external accretion event and gas came into the galaxy to generate this misalignment. That's the main thing to remember. That we can use this misalignment to infer the past history of a galaxy. So how does this connect with black holes? So I told you in the beginning, we're interested in knowing how black holes are fed, how are they fueled. So the question that I was very curious about and I wanted to address in my work was, can these galaxy interactions and the fact that they generate this misaligned gas, can they contribute to the fueling of black holes? Can this gas flow through the galaxy due to the misalignment and then actually fall into the black hole and feed both the growth and the activity of the black hole. So this is what I wanted to investigate. So for the rest of the talk, I will tell you how we did this and the results that we obtained. So this is the connection between galaxies and the growth of black holes. And is this a fair thing to look into? Does it make sense? So if we think of how much gas is needed to fuel a black hole, the first time that I did these calculations as a PhD student, I was actually surprised that you don't need a lot of mass to fuel a bright AGN. So if you have the brightest active galactic nuclei, quasars, we need a fraction, 10% times the mass of the sun to 10 times the mass of the sun per year to fuel the activity of these very bright quasars. But if we look at moderate luminosity AGN, which are the most common ones in the neighborhood of the Milky Way, we need only a small fraction of solar mass per year to feed those black holes, to feed that activity. And if you think of, for example, a dwarf galaxy that merges with a bigger galaxy, the mass of gas contained in that dwarf galaxy may be enough to fuel a low luminosity, moderate luminosity AGN for maybe up to a giga-year. So one of these interactions can actually provide enough fuel to power an active black hole for a significant amount of time. So it's a scenario that could possibly be efficient in terms of powering active black holes here. Okay, so I showed you this image before. This is one of the examples of misaligned gas in stars. But this is a striking image. Unfortunately, not all galaxies with misalignment look like this and are not as easy to identify. What we can do is to use integral field spectroscopy, which is a technique for observations where we can obtain enough information to determine how the stars and the gas are moving in a galaxy. So here in this image, this is from the Manga survey, is one of the biggest integral field spectroscopy surveys of the local universe. So here in the background, you see an image of a galaxy, and the circles on top represent fibers for which we can obtain a spectrum. And what this allows us to do is, for each spectrum, we can extract the information about the velocity of the stars and the gas. And if you do this for the entire galaxy, then you can determine how the gas and the stars are moving. So what we do with this, for the purpose of our research, is to extract velocity maps of stellar and gas to allow us to determine how are the stars and the gas moving and are they misaligned. So here in this figure, I'm showing an example of how we do this. So the y and x axis are just the size, physical size of a galaxy. So this is just probing one galaxy. On the left, this is the map of the velocity of stars, and on the right, a map of the velocity of gas. So these are 2D maps because we can probe motions at each location.
Esperemos que no se pierda, porque no sabes tú quién puede pasar por ahí, verla y decir, bueno, aquí se la han dejado, pues mira, una tablet para mi hijo, que me quedo, qué bien. No, pero cualquiera que haya por ahí puede pasar y verla. O tu compañero tuyo. O sea, primero, la primera tablet te la cargaste, o sea, bueno, es esta misma, ¿no? Que sigues usándola. Bueno, yo que tú llamaría a consejería y me aseguraría que se pasa. Bueno, se puede llamar, ¿cómo que me llamas a mí?
So this misalignment of 180 degrees is counter-rotation. So this is one of the galaxies where the gas rotates in a completely opposite direction to the stars.
Sí, claro. Para decir que por favor que te has dejado la tablet, que la lleve a la consejería para que mañana te pases a primera hora. Para eso tienes que ser mayor de edad. Yo estoy trabajando, hijo.
This is the method that we use. So now I will give you some examples of how we can.
Hombre, hijo, vamos a ver. No hago nada, ¿no? Es tu responsabilidad, tú la has olvidado, tú tienes que llamar. No es tan raro, ni tan grave. Llama tú, si te dicen que llame yo, llamo yo, ¿vale? Sí, claro, me parece justo, ¿no? Y te dicen, no, mira, tienes que llamar a tus padres.
And this is looking at the very inner regions of the galaxy.
Venga,
So
hazlo, inténtalo.
10 kiloparsec or so. So this black cross
No, al revés,
shows
intenta
the
llamar
position
tú
of
y
the black
si
hole,
no te lo cogen o
and the
te,
color scheme is the same as the figure before.
te da
So
vergüenza,
what you
es
can
eso.
see is that just
Bueno,
looking
pues
at the stars in
bueno,
this
pues lo
galaxy,
siento, no pasa nada, tienes que hacer un esfuerzo.
the
No,
central
por eso
region
cuando te lo digan llamo yo.
counter-rotating. So here the
Ya,
arrows show
pero
the
como
direction
lo has
of
perdido tú,
rotation
lo
in the
responsable.
central region within the
No,
ellipse,
el responsable, el esfuerzo lo tienes que hacer tú, que es el que se lo olvidó. Llama tú, mira el teléfono, busca en internet consejería y sapere aude. Y cuando, si te dicen que tú no puedes llamar y que no quieren saber nada de ti, entonces me lo dices y yo llamo.
Something happened in the past history of this galaxy, an external accretion event that created this counter-rotating core of stars. So then what we can also do is to look at what is the gas doing in this galaxy. And we look at the molecular gas. So molecular gas is important because we know it's the reservoir for the formation of stars, but also we think it's the reservoir for the fueling of the black hole. Basically the gas that is available for both the formation of stars, but for the black hole to grow as well. So we looked at the molecular gas in this galaxy. Again, this cross here shows the position of the active black hole, the AGN. And if you compare the direction of rotation of the gas, blue, red, you see that it's rotating the same way as component 2 here. So it has the same direction of rotation as the counter-rotating core of stars. So in our analysis, we saw that the molecular gas and these stars are connected. So they were connected to the same external accretion event that happened in the past history of the galaxy. One interesting thing is when we look at the gas, the dominating component, as you can see here, is this counter-rotating gas. So this external accretion event basically replenished the reservoir available to the galaxy, to the black hole, and it's all counter-rotating. And what we think happened here was that this gas came into the galaxy, it settled in the disk, and then it formed stars. And because stars inherit the kinematics of the gas from which they formed, they were also counter-rotating. So this is what we think happened in this galaxy. So how can we relate this with a black hole? So what we did was this is the reservoir of gas that we have now. It's all counter-rotating. And we calculated that there was 4 times 10 to the 7 solar masses of molecular gas there. And if we consider the rate of gas accretion, current rate of gas accretion for this active galactic nucleus in this galaxy, it would be enough to fuel the black hole activity for 2 billion years. That's a long time. But we could also do something interesting, and that is to look at how efficient the process of black hole fueling is. If you get all this gas in, then how do you divide the gas budget in terms of gas that goes to form stars or gas that goes to fuel the black hole? So we calculated that the gas mass used to fuel the black hole was only 1% of that used to form stars. So it's actually not a lot of gas that is needed to power the black hole. So in terms of efficiency, it was much more efficient in the formation of stars than the fueling of the black hole. But that was, however, enough to fuel the black hole for 65 million years at least. That's our estimate. So in terms of the efficiency, only 1% of the gas mass is enough to power the black hole in this galaxy. So this is one of the things that we can do when we discover one of these misaligned structures in a galaxy. So let me show you another example, and this is starting from numerical simulations. So these are simulations by Van der Voort and collaborators, and what they did was to look at misaligned gas and external accretion in a simulated early type galaxy. So they start with the galaxy. So here, these panels show the evolution of the simulations from left to right, top to bottom. And they start with a galaxy that has these white contours show the stellar distribution of the galaxy, and the colored data points are the gas particles. And the color coding is the same as before, so it has to do with the direction of motion of the gas. So blue motion towards us, red motion away from us. So they start with a galaxy that goes through gas-rich merger with another galaxy, and then it forms so many stars that the supernova feedback removes the gas from the galaxy. That's at step 2. But because there's still gas around the galaxy, there can be minor mergers, the galaxy can still accrete more gas. But when that happens, the gas comes in misaligned, as you can see here. The interesting thing about the simulations is that they show that with time, the gas will align with the disk of the galaxy. And this is due to stellar quarks acting on the gas. And this is interesting because it's telling us that there's a mechanism causing the gas to lose angular momentum and flow to the center of the galaxy. This is what we want if we want to feel black holes. And these numerical simulations are very interesting. And what we found from observations is that there was one galaxy where we saw something that had been predicted by these simulations. So here in the left, I'm showing a map of a galaxy, MGC 5077, and this is the distribution, the velocity distribution of the gas in the galaxy. And it resembles this stage here in the simulations where you can see there's some alignment in the center of the galaxy, but then there's these tails of gas here to the north and to the south of the image, which shows that this galaxy is likely in the stage where the misaligned gas is slowly aligning with the stellar disk of the galaxy. So this was the first time that the predictions from these numerical simulations were seen in observations. And this shows that there's a process of aligning the gas that starts at small radii and then it goes to large radii. So it's a process that slowly is causing the gas to lose angular momentum and aligning with the stellar disk of the galaxy. At some point, it will end up aligned with the stellar body of the galaxy. But this is another example of how we can use this misaligned gas to infer the past history of the galaxies, but also the potential impact that it can have on the central supermassive black holes. Okay. So I showed you some examples, concrete examples from individual galaxies, but we wanted to determine, is there a connection in a statistical sense? So if we look at a large sample of galaxies, do we see an influence on galaxies that have misalignment in terms of how active their black holes are? So to do this, we could use the recent integral field spectroscopy surveys because it allowed us for the first time to have access to thousands of galaxies with the needed information for us to extract two-dimensional maps of stellar velocity and gas velocity, because we need that to determine if the stars and the gas are misaligned. And we need large samples because not all galaxies have interactions, not all galaxies have misalignment, so if we want to get a statistically significant result, we need to start with a large parent sample. So our goal was to then go one step further and say, or ask, in a large population of galaxies, do we see a correlation or connection between stellar and gas misalignment and the fraction of active black holes? So again, I've showed this figure before. This is just a reminder of how we actually measure these misalignment angles. So we do this, and we can do this for all the galaxies in the parent sample. And then what we did was to separate the galaxies in two groups. So the first group, which is here on the left, are the galaxies that show small misalignment angles, so between 0 and 45 degrees, which means that within the uncertainties of the measurements, they have their stars and the gas rotating in the same direction, so they are aligned, which means that we cannot be sure if they had a past external interaction. And then we have the second group of galaxies that have a very large misalignment angle, so higher than 45 degrees, which will be here on the right. And for these galaxies, because the misalignment angle is so large, we know that there was an external accretion event in the past history of the galaxy that resulted in this strong misalignment. And then we measured the fraction of active black holes, AGN, in each of the two groups. So what we found was that there was a significant increase in the fraction of active galactic nuclei in galaxies that had misalignment. And this is significant to 3 sigma level. So it's a much higher fraction of AGN than in galaxies that are aligned. So this shows that AGN are more common if misalignment is present, which points towards a connection between these two processes, that if you have misalignment, that is connected with the activation of the black hole. So this was the first time that this was seen for these kinds of galaxies. We didn't know before that there were more AGN if you had misalignment. This suggests that having misaligned structures is a candidate fueling mechanism to power black holes. So basically to provide what we need to fuel black holes, the gas, and then the mechanism to transport the gas to the center to fuel the black hole. So when we looked at what types of galaxies were dominating this trend, we found that it was the early type galaxies. So early types are ellipticals and S0s, so they don't have a lot of gas to start with. So it wasn't, thinking about previous work in this field, it wasn't surprising that we found that early type galaxies were dominating morphology in our sample. Because previous studies, when looking at early type galaxies with gas, they found that around 40% of them have misalignment. So misalignment is much more common in early type galaxies than late type galaxies. And it makes sense, because if you think of, an early type galaxy does not have a large amount of native gas to start with. So if you have a thermal interaction that brings gas to the galaxy, it can replenish the fueling reservoir, and the misalignment will also be long-lived, because there's not a lot of gas to dissipate that effect, or it doesn't do so very quickly, so it's long-lived. While for late-type galaxies, and these are spirals, they have larger amounts of gas. If you have gas coming in from the outside, it's unlikely that the amount of gas coming in will dominate over the amount of gas already in the galaxy. So what happens is that there will be dissipation, and if there's misalignment, it will be short-lived, because the gas coming in will dissipate its energy with the gas already in the galaxy. So this makes some sense in terms of early type galaxies being the morphological type of galaxies for which this mechanism is more important. And then I showed you some numerical simulations that show how this misalignment and the stellar torques can contribute to the flow of gas to the center of the galaxy. But there have been other simulations pointing in the same direction. So when there are structures, misaligned structures, that could be structures in the stars or the misaligned gas, that there's an increase or promotion of the inflow of gas to the nucleus of the galaxy. And this can be done via gas dissipation, via stellar torques, as I showed you in the previous simulations, or via shocks in the gas. So this contributes to the flow of gas to the center, which is what we want if we want to fuel the black hole. So going back to what I mentioned in the beginning of the talk, that if we want to fuel black holes, we need a gas supply and the mechanism to drive gas to the black hole. The misaligned gas to stellar configuration can actually provide us with both. So there's an extra gas supply that came from the outside, and then the fact that you have these misaligned structures, that can be the mechanism that is causing the gas to lose the angular momentum and then flow to the center. While the simulations don't have the resolution to show if the gas actually goes all the way to the black hole, our observations that show a higher fraction of active black holes show that it's very likely that this gas is actually falling into the black hole and promoting the active phases. So we did this as well for the Mango survey. So we started with the Tiny survey, we used the Mango survey, and we find the same trend. So this trend is present no matter which survey we choose. These are both local surveys, but they're slightly different in the stellar mass range probe, for example. What we wanted to test as well was how we select AGN. So for this work, we selected AGN in a slightly different way, but it didn't affect the trend that we see. So we still see a trend of a higher fraction of AGN for galaxies with misalignment in the Manda survey, which is 10,000 galaxies as a current sample. So the trend that we see is robust. And then also we're curious about what kind of AGN do we have here, and what is the AGN luminosity, how luminous are they? So this was work led by Martina here from the University of Southampton. So Martina is an excellent master's student who has been working with me for the past year, and she's soon going to become a PhD student at the University of Durham. And her research was focused on measuring the luminosity of these AGN and seeing if there was a trend between how luminous an AGN was and how misaligned the host galaxy was. So this figure is from her work in preparation for publication, and in the y-axis, this is the O3 luminosity. So this is a good probe of the AGN luminosity because the O3 emission line requires a high excitation potential. So this is a proxy for AGN luminosity, and the x-axis shows the misalignment degree between gas and stars. So this vertical line shows the division between aligned galaxies, which are the ones on the left, and strongly misaligned galaxies. Early types are shown in purple and late types in green. So Martina found several things in her research. So she found first that there was no clear trend between AGN luminosity and misalignment angle. So there wasn't any preferred angle at which AGN were more luminous. So this goes towards that idea when I showed the numerical simulations that the misaligned gas is slowly aligning with disk, and it probably is a very long process where the gas is slowly funneled into the black hole. So it takes a long time for the black hole to be fueled, but always at a relatively constant level in terms of luminosity. She saw that as I mentioned before, late type galaxies tend to be in the aligned bin. Most of the, or all of the misalignment is due to the early type galaxies. But what she also found was that if you look at the luminosity range for early type galaxies, it's not as wide as the luminosity range for late type galaxies. It's narrower, but it seems to be relatively the same no matter if you look at early type galaxies in the aligned region or misaligned. And this led us to conclude that probably these early type galaxies are also being fueled by the same mechanism, also by external interactions, but the gas and the stars end up aligned. So likely all these early type galaxies are being fueled, or the gas is coming from external interactions, because we don't see a difference in terms of the AGN luminosity. And then something that is also important for us to check was the role of outflows. And for those who work on AGN, we know that if the AGN are powerful enough, they can drive outflows, and that can affect the dynamics of the gas in the galaxy. So it's important to think, is the misalignment that we're seeing actually caused by something outside in, or is it the AGN that is disturbing the gas so much that it's causing it to be misaligned? So there's several evidence from our work that it's an outside-in process, and it's not the AGN driving outflows that is affecting what we see. So one of the reasons is that the AGN that Martina measured the luminosities for, they're relatively low luminosity. We don't have the very bright quasars in our sample. We also see the misalignment at global scales of the galaxy. So we're seeing that the gas is misaligned at hundreds of parsecs scales or kiloparsec scales, and not small scales. So, and to add to that, we also looked at the velocity dispersion of the gas. So the velocity dispersion of the gas that I'm showing here is used to trace AGN outflows. So when we see very high velocity dispersion in the gas, that indicates that there's probably an AGN outflow affecting the gas. But what we see in our sample is relatively low velocity dispersions in the gas, and we don't see, when we do a statistical analysis to see if the populations are different, we don't see any difference between AGN and misaligned or aligned galaxies, or even galaxies that have no AGN but have misaligned gas. So from our analysis, the AGN outflows are not driving the trend that we see. So it's an outside-in trend and not the AGN outflows driving the misalignment. We do see that some AGN may have an influence in the unresolved, very small-scale region around it. So we see in the unresolved central pixels, we see an increase in velocity dispersion. So maybe these AGN have some influence, and this is seen from other works, in the very, very central regions, but not at the scales where we're measuring the misalignment angle. Okay, and then another thing that we wanted to do was to try to investigate if we have these two processes connected, because we know that misalignment was generated by an external accretion event, how can we say which one of them is actually causing the higher fraction of AGN we observe? Maybe it's just because galaxies have more interactions and they will have a higher number of AGN. So to study this, what we did was to start with a parent sample of manga galaxies, but then we selected only the ones that had signatures of mergers or interactions in their images. So this is the sample that we know had a past interaction. And then our idea was, let's look at the fraction of AGN in galaxies within this subsample with aligned and misaligned gas and see if we still see a difference in the AGN fraction. So when we did that, the difference, of course, naturally is smaller, but we still see an increase in the fraction of AGN here on the right in galaxies with misalignment. So it means that even if you look at galaxies that had recent interactions, there's still a further increase in the AGN fraction. So this means that the main driver for this trend is the misalignment in the gas and the stars, and not only the mergers or the interactions, which are important. We still see that if we're looking at the galaxies with the mergers, they have a higher fraction of AGN to start with, but the increase then when we look at the ones with misalignment is still significant. So the main driver for this AGN fueling mechanism is misalignment between gas and stars. Okay, so let me conclude. So I discussed how black holes are fueled. This is one of the mechanisms that we can study and that we found some evidence for it. I showed you that if you have external gas accretion, that it can replenish the gas reservoirs that galaxies have to fuel their black holes. And that when that interaction results in a kinematic misalignment between stars and gas, then we see a higher fraction of active black holes. And the main driving mechanism for this increase in active black holes is the misalignment. So the result from this is that we are looking at an important mechanism to fuel black holes, where we have a supply of gas and also dynamical mechanisms or mechanisms due to these misaligned structures that are contributing to the gas to lose angular momentum and flow to the black hole and fuel the black hole. And this is a mechanism that is likely particularly important in early type galaxies. So I have to highlight that there are other mechanisms to fuel AGN. Of course, not all galaxies would have had interactions or misaligned gas, but this is one where we could find evidence for it, and it's particularly important for early types. And if we can think of how this changes with redshift, all the samples that I showed you today, these are all local galaxies. But if we think of galaxies at high redshift, where we know that galaxy interactions are more common, then it's likely that this mechanism would have been more important at high redshift. Okay, thank you.
Thank you very much, Sandra. Very comprehensive talk. I enjoyed it a lot. So we have time for questions. You can unmute your microphone if you wish and ask your question. Well, I have...
Yeah, I can ask a question. I can't find the raise hand button now the Zoom has changed again. Yeah, thanks for the great talk. So I was, this is probably a simple answer to this, but I was wondering what the fraction of AGN are in your sample that split between early and late type galaxies. because if the misalignment is more common in the early type galaxies, and then if the AGN were more common also in the early type galaxies, how would you account for that effect?
Well, that's a good question. They are 50-50, so roughly 50% of them in late types and early types. I have to highlight that that's not what we typically see when we look at galaxy morphology, but these are early types for which we can measure the misalignment, which means that they have gas. So what we can say is that if you look at early type galaxies with gas and late types, the AGN are distributed 50-50.
Okay, super, thanks.
Yeah, Maritza? Go ahead.
Hi, Marita.
Hi, very nice to meet you.
Nice to see you.
So I was wondering if you have checked the environment of your sample, to see if most of your elliptical galaxies belong to groups or even filaments. For instance, in some galaxies you should have like a very nice environmental catalogs that comes also from the gamma sample. So I mean that following that, so I wonder if your elliptical galaxies that have an AGN and misalignment, they do also belong to, for instance, groups of clusters of galaxies.
So they are mostly in groups or isolated galaxies. So they're not in clusters, these ones. So the misalignment is not present in clusters, it seems. And you were asking if the late type galaxies with AGN were in clusters? Was that the question? The second question?
Yes, yes.
I haven't checked. They're not that many. So you said misaligned, right? Misaligned late types with AGN. I think there's only one in the semi-survey. There are more in manga. Sorry, let me go back. Yeah, so there's only one late type galaxy, and I don't remember the environment for this one, but in manga there are more, so it's something that we can check. That's actually a good idea, Melissa. We need to check that.
Thank you.
Well, I have one question. You mentioned, Sandra, before the stellar torus and also the dissipation and shocks as a mechanism to fueling the gas within the black hole. What is the role of the bar in your sample? Could they be?
Yeah, that's a good question. We haven't looked at all at the presence of bars. We saw, well, Martina got very excited with the images of how the gas was distributed, and she found that some had bars and some had nuclear rings of star formation, but we didn't look at it further. So we didn't do any statistical analysis to see if they had more like substructure that could also help fueling the black holes, funneling the gas to the center, with the bars. But that's interesting. We haven't looked at that further than noticing that there was some of them that had these structures. We haven't done the analysis yet.
Thank you. Well, other questions? Yes, fine. Well, I have another one question. I was wondering how you can distinguish between, let's say, gas that comes in and gas that, let's say, go out of the galaxy. When you mentioned the velocity dispersion maybe before.
Yeah, so that's the main diagnostic that we use, is looking at the velocity dispersion. Because it's relatively low, so it's very unlikely that it's being driven either by AGN outflows or supernova outflows. And also we see that it's a global, when you look at the velocity of the gas, it's kind of a global rotation of gas. So we're not looking at small scale disturbances, but it's basically showing red, blue at scales of hundreds of parsecs. So it looks like rotation. And combined with the velocity dispersion, that led us to think that it's something from the outside coming in and not inside coming out. And also with the simulations, seeing that when you have gas flowing in, you can get these configurations. That also supports that idea that we're seeing gas coming in. So inflow instead of outflow.
So you don't have any evidence of major measure in your sample?
So for this sample here, we did that. So for this one, they all have evidence of mergers or interactions. So these ones were selected to have in the images some features like tidal tails or any other signs of interactions. So all of these, at least for this subsample, they had signs of external interactions. And then we measured the misalignment for those.
Well, the majority of the mergers are minor.
Yeah. So these signatures,
like a stream flow.
So for these ones, minor mergers are also included. Major minor mergers are in the signs of tidal interactions. Along the filament, I don't know if that's actually included because I don't know if you can see that visually in the deep images. I don't know, do you know if you can see features, if there's like a filament, if you can see features in the images? I don't know if they will be included in this sample, to be honest. Yeah, so maybe they're not in this subsample.
Thank you. So any other questions? Well, if not, I think we can thanks to Sandra again.
Thank you, it was a pleasure.
And thank you everyone for joining us. See you. Bye bye.
Thank you. Bye bye.
Bye.
Bye, Sandra.